It's time for fun with math, and today we're going to talk about power series. So what is a power series? And let's motivate this with something we've already done. So we've already talked about geometric series. So in particular, we looked at this infinite sum, the sum n equals 0 to infinity of a times r to the n, which remember was just equal to a plus a times r plus a times r squared plus dot dot dot, and this is actually equal to a divided by 1 minus r as long as the absolute value of r is less than 1. Now I'm going to make a few changes here. We're going to let a be equal to 1, and instead of thinking of r as a number, let's think of r as being a variable. So let's let r be equal to x. And if we rewrite this, what we get is the sum n equals 1 to infinity of simply x to the n. And when we write that out, we have 1 plus, oh, this is a 0 down here, sorry. 1 plus x squared plus x cubed plus dot dot dot, on and on forever and ever. And this right here, this expression right here, 1 plus x squared plus x cubed, this is an example of a power series. So a power series, the idea, it's kind of like a polynomial. In fact, a polynomial is an example of a power series, but a more typical example would be a polynomial that never ends. So you think about this as like a polynomial that never ends, and that's what we mean by a power series. And the idea is that sometimes you can find a power series that represents a function, because over here, if you let a be 1 and r be x, we know that these two things, the power series on the left and this rational function on the right, are the same as long as x, absolute value of x, is less than 1, which means basically, right, remember that implies that negative 1 is less than x is less than 1. So if you graph this between negative 1 and 1, and then you try to graph this, now when you graph a power series, you can't graph the power series itself typically. You have to graph sort of like a part of the power series. But if you graph this like up to x to the 100th, basically these two graphs will look exactly the same. So this is sort of an example, this is a typical example of what a power series is, and the fact that it's equal to a function on some interval is how we'll be using these later on. But first, let's talk a little bit more about power series. We talked about what a power series is. Let's take a look at the definition so we can learn a little bit, a little terminology here. And so a power series centered about or centered at x equal a is given by this type of formula, where the c sub n's are real numbers. So, don't be afraid of this. The idea is just basically, you can write n equals 0 to infinity. You have some c sub n's here, so, maybe c sub n is just 1 divided by n. And then you have x minus, and it's centered at some number, so maybe the number is 2. So x minus 2 to the n. So if you wrote this out, it would simply be, n be equal to, let's change the index down there because it really doesn't make sense if it's 0 because you can't divide by 0. So let's start at 1. So if you start this at 1, then when you plug in 1, you get 1 times x minus 2 plus, now plug in 2, you get 1/2 x minus 2 quantity squared plus, let's do one more, plug in 3, so 1/3 x minus 2 quantity cubed, and then plus dot dot dot. And so this is an example of a power series. It's centered at the number 2. So it's centered at the number 2 here because you're doing x minus 2. And we don't know where it converges. Actually, that's what we want to figure out. And in the end, we want to know, when does this converge? And so that's one of the questions we'll try to answer in this section. But first, let's look at a couple more examples. So I got a bunch here for us to do today. So I have 4 examples. Now realize these are all power series because you're adding just basically powers of x. So again, it's like a polynomial that never ends. You just write dot, dot, dot. notice they're centered at different places. This one's centered at 0, this one's centered at 0, this one's centered at 0, this one's centered at the number 3. So you could say this is a power series about 0 or centered at 0. You'd say this is a power series again centered at 0 or about 0. But down here at D, you'd say this is a power series centered at 3, or you'd say a power series about 3. So what we want to do in this problem is we want to find a closed form for each of the power series. So the idea is we want to rewrite each of these power series as sort of the sum n equals 0 to infinity of some number c sub n times some x minus a to the nth power. We want to find that closed, this is called a closed form. So let's do that. So let's take a look at our first example. Find a closed form for the power series. And there's several ways to do this. You might be able to look at this and write it down right away. I'm going to give you a little bit of a strategy to follow. So I always like to make a table if I'm stuck. Now, of course, on this one, I'm not stuck, but it's easy to show you sort of the strategy to follow in this one. And so the idea is you have your sort of n, and then over here you have your sort of c to sub n. And so now what are you going to do? You say, okay, well, if n is 0, you get out this number 1 right here. If n is 1, you get out just x. If n is 2, you get out x squared. And when n is 3, you get out x cubed. And so you're looking for a pattern. So like if you plug in n, you want to see, well, what am I going to get out of here? And so if you notice on here, you can kind of see how the numbers going in line up with the exponents coming out. So if there's a 1, there's a 1. If there's 2, there's a 2. There's 3, a 3. And even 0 lines up because remember 1 is x to the 0. So I would guess the formula for my little c sub n here is actually x to the n. And so when I write down this power series, we'll call this s of x equal to this. I can write down simply s of x is equal to the sum n equals 0 to infinity of these terms x to the n. And now, of course, I could have done that just by looking at this, but this is sort of the strategy you can follow. You can just make a table and try to find the formula. Let's look at the next one. So in the next one, again, we want to find that closed form for the power series. So we'll call this s of x. And this one's a little harder to see. So if you can't see it straight off the bat, what you can do is you simply make a table. Here's my n, and here's my c sub n's. And I start at 0, and I get out the number 1. And then I start at 1, and now I don't get out plus, but I get out minus x squared over 2. And then I plug in 2, and I get out plus x to the 4th divided by 4. And if I plug in 3, I get out that last term they give me, so negative x to the 6th divided by 6. And so the question then is what happens when you plug in n? All right, so we basically want to know what's going to happen here. I'm going to draw through this. What happens when I plug in the number n? All right, so you look for a pattern here. And so I noticed if this is 1, this is 2. If this is 2, this is 4. If this is 3, this is 6. All right, so the bottom seems to have some sort of pattern to it, but I'm going to draw a line here. And so let's see. I think before I do 2, 4, 6, I'm going to go back here because if I do 1, I get x squared, x to the 4th, x to the 6th. So they all have an x in it to some power. So I draw an x here. And so if it's 1, it's 2, it's 2, it's 4, it's 3, it's 6. So those are even numbers. So how do you get even numbers up there? I think it's going to be 2 times n. And that's my guess, and let's just check it. So, you know, this one is like 2 times 1. This one would be 2 times, let's just right here, let's think about it. This would be 2 times 2. This one would be 2 times 3. So that checks, right? So that one checks right there. Now, I also have, it goes plus, minus, so that's going to be a negative 1 to some power. Now, the power, I'm going to try n first to see if that works. And so if you plug in 0, remember negative 1 to the 0 is just 1. If you plug in 1, you get negative 1. Plug in 2, it's pop, so that works. So that gives me the pluses and minuses. So I have the power of x, right? So remember this one here is really x to the 0, if you think about it, because that's when n equals 0. And I bet this one here, you can say it's divided by 1, maybe. So let's see. I'm just missing, I think, the bottom, right? So the bottom looks like here, if I thought about it, goes 1, 2, 4, and 6. So 2, 4, 6 I can get. This 1 might be a problem, but notice 2, 4, and 6 are just, again, even numbers. In fact, it matches up with the top. If a 2, a 2, a 4, 4, a 6, 6. Oh, so this should be 2n also. The only problem is this sort of leading term doesn't match up, because if you plug in n equals 0, you get 0 in the denominator. So what you're going to do is we're just going to cut it off right here. So when I write down this sum, I'll write down s of x equals, that 0 term, I'm just going to put it in front. It's 1 plus, and now I have this closed sum, this closed form, n equals, we'll pick it up at 1, we'll go to infinity, and now the formula should work. We have negative 1 to the n, divided by 2n, and then all times x to the 2n. And so there's the formula for this closed, for this power series. This is the closed form for the power series. All right, so that was a little bit tricky. Let's try another one, though. Because after we do a couple of these, you see they're all kind of basically the same. I think I'm going to put my table over here so I have a little bit more room to work. So here I'm going to put my table. I have n and c sub n. And I just start this off. Now, here you have to be a little bit careful because you don't have a constant term. So I'm going to start my n at 1. And so here I have 2 divided by 1 factorial x. Over here I have 4 divided by 2 factorial. Oops, I'm sorry. I have the number 2 over here. I have the number 2 on this side. So then I have 2, and I have 4 divided by 2 factorial x squared. And then 3, I have 6 divided by 3 factorial x cubed. So I'm just writing down n, which is the number of term, basically the power of x usually. And then I have on the right-hand side what's happening there. So like the fourth term right here would be this one. And oops, there's a mistake right there. I think that should be a fourth power. So let's change that to a fourth power if I haven't changed it already on your paper. And so that's 8 divided by 4 factorial x to the fourth. And then one more, 5. I have 10 divided by 5 factorial x to the fifth. Now, if you can't see a pattern emerging here when you do n, you can always try to create the next term. And as soon as you create the next term, your brain basically has the pattern. You just have to pull it out of it. So, you know, if you look at this, it's like 2, 4, 6, 8, 10. Oh, the next one on top would be a 12. And it goes 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial. Oh, the one on the bottom must be a 6 factorial. And then here you have x to the x squared, x cubed, x to the fourth, x to the fifth. I bet this is x to the 6. So as soon as you can do that, your brain has captured the formula. Now you just have to force it out, basically. So again, the idea is just write down what do you think would happen if you have n here. And so what you want to notice if you have one, so again, just copy all the commonalities first, right? So it's like, oh, there's a divided by, there's an x to the, there's some sort of factorial, and sort of fill in the blanks, right? So the power is usually pretty simple. 1 and 1, 2 and 2, 3 and 3, 4 and 4. So it's n, you put in. And notice the denominators here are the same too. 1, 1 factorial, 2, 2 factorial, 3, 3 factorial. So it's n, I bet it's n factorial. And then finally, the top number, if it's 1, it's 2, it's 2, it's 4, it's 3, it's 6, it's 4, it's 8. Oh, so you're multiplying the inputs by 2, so I bet it's 2 to the n. And you can check then this with any of the preceding examples here, and you'll see that it works. So my sum, let's come back up here for a minute. This is going to be my s of x, so we'll call this s of x. My power series, if I want to write down the closed form, using this sort of sigma notation, I can write this as n equals 1, because you start with this x term, to infinity, of what? Of 2n divided by n factorial x to the n. And so there's a formula for that sum. And so then the next one more we're going to do. Let's look at this one. Again, let's call this s of x. And if I want to find that closed form, if you can't just, if you can look at it and do it, there's no problem. But it's really good to practice just making a table. It's easy to make. You have your inputs here, and you have your outputs over here. And I guess I shouldn't call these C sub n's because they're not really C sub n's. They're like C sub n's x to the n. All right, so maybe I should go back up and actually correct that, right? So they're really like these C sub n's x sub x to the n's. All right, so here you do have a 0 term. There's no x here, and this one's centered at 3. So actually, we can even correct this further if we want to. Instead of writing that as x, we should probably write that as x minus 3 to the n. And so what are we going to do? We have a 0 term, and so for the 0 term, there's a 5. For the first term, there's 7 times x minus 3 divided by 2. For the second term here, we have 9 times x minus 3 squared divided by 4. And then for that third term, we have 11 x minus 3 quantity cubed divided by 16. And so again, we want to figure out what happens for n, but if you get stuck, you could try to do the next term 4. So the idea is, well, there's definitely a division. If it's 1, it's 2, it's 2, it's 4. If it's 3, it's 16. I don't know if you guys see the pattern there, but it's like 2, 4, 16. So what I see is I basically have 2 to the first power, 2 to the second power. Well, that's not quite 2 cubed, right? So this is 2 squared, 4 squared, 1 squared. So that doesn't quite work, which is making me think I screwed up when I wrote this down, right? So this actually is a mistake. Let's fix it. This should be an 8. This should be an 8. Otherwise, the pattern isn't correct. All right, so now this is a little bit easier to see, okay? So right here, remember, you do have an x minus 3, but it's to the 0 power. And there's a 1 down here. So this would be 2 to the 0, 2 to the 1, 2 squared, 2 cubed. Aha! This would be 2 to the 4th, which would be the 16. And then this is 5, 7, 9, 11. I bet this one is 13. And then this is x minus 3 to the 4th. All right, so now everything matches up. And so when the problem is given to you correctly, the formula is not terribly difficult to see. So if you plug in n, I'm thinking here on the bottom, you're going to have 2 to the n. Because that's, 2 to the first, 2 squared, 2 cubed, and 2 to the 4th. So it's n, it's just 2 to the n. You certainly will have an x minus 3 to the nth power. Because here, if it's 0, it's 0. If it's 1, there's a 1 here. We don't usually write 2 to 2, 3 to 3. And now I just got to figure out what this sequence is, 5, 7, 9, 11, and 13. Now, those are odd numbers, but you start at 5. So what you want to realize is if here you start at 5, the next one you add 2 and you get to 7. Then you add 2 more and get to 9. So each one you're starting at 5 and you're adding 2's. So the way you write that down is you say 5 and you're adding 2 n times. So that's a little bit tricky, so think about it. You have this pattern, 5, 7, 9, 11, and now 13. How do you write that down as a formula? Well, you start at 0, so 0 gives you 5. This is 5, then you add 2 if it's 1, so it's like 2 times 1. This is 5 plus you add another 2, so it's like 2 times 2. And this is 5, and you add another 2, so it's like 2 times 3. And so now the pattern, or the form, hence the formula, emerges. All right, so it's 5 plus 2 times 4, so this is going to be 5 plus 2 times n, whatever your n is. And so now I can write down this formula. It's the sum n equals 0 to infinity of what? Of 5 plus 2n times x minus 3 to the n. And we can divide that all then by 2 to the n.